All right, how's everybody doing so far? So far, so good? Okay, all right. Okay, before we get started today, I wanted to tell you a little bit about two things that the home base is offering. So the first thing is they have some help for submitting your application for the next school year. So if you're thinking about doing a financial aid application for next year, the home base can help. So there's this pamphlet up here, and there are a couple of days and times listed. So their hours are listed. Really, you can go in anytime when they're open, and they will help you out with the financial aid application process. So that's a great resource, and I mean, it's free money, so there's no reason not to do it, okay? So definitely check this out if you're interested in financial aid for next year. The deadline, I think, for applying is March 4th, so that's coming up. That's less than a month away. So you might go and talk to them about that if you're interested. And then also, they have seminars where they can help you with earning or applying for a certificate or for graduation. So this is a beginning class. Most of you probably aren't ready to graduate yet, but this is a class that's part of a certificate program. So you might be close to earning a certificate. So if you are interested in applying for a certificate, there are several days and times listed here when they have specific help with that. So you can definitely check that out as well. So both of these pamphlets are up here on the board, and you can come and check out those days and times if you're interested in financial aid or certificates. So any questions about that? All right, then today we're going to start with a review of Ohm's law. We talked about Ohm's law last time. We said that that's the most important law in electronics. It's the foundation for everything else. It's the relationship between voltage, current, and resistance. So we're going to do a quick review of that. Then we'll go on to our main topic today, which is series circuits. So series is when two or more components are connected end to end, almost like trains on a train track, okay? So we'll talk about what that is, why it's so important, and then we'll play a quick game. So we'll look at a couple different circuits and try to figure out whether they are in series or are not, okay? So hopefully that'll be fun. And then we'll talk about series resistance. So if you have two or more resistors in series, you can find their total resistance. We'll talk about how to do that. And then we'll look at how we can use Ohm's law when several components are in series. And this is very important because many circuits in the real world are in series. And so if we want to understand them, we need to understand how to use Ohm's law with series circuits like that. And then we'll go on to a slightly different topic, which is engineering notation. Engineering notation is how we can use abbreviations to write very large or very small numbers. So when we talk about like kilobytes in a computer or milliamps, those abbreviations stand for different numbers. And they can allow us to write very large numbers or very small numbers without having to write tons and tons of zeros. That is easier for you, and it also makes it easier for somebody who's trying to read it. You know, they don't have to squint and count whether that's 7 or 8 zeros. They can just look at a prefix and know what's going on. So we'll talk about what that is and how we can use that. And then we'll go on and do a preview of today's lab. So in the lab today, no surprise, you'll be getting to work with series circuits. So you will do some series circuits in Multisim, and then you'll also build some series circuits on a breadboard. So that's what we'll be doing today. And then for homework, I'd like you to work on the metric conversion homework in the lab book on page 61. So this will be a chance to practice some of those engineering notation that we talked about in class. It'll be how you can convert from one engineering notation to another, like kilobytes to megabytes, or milliamps to microamps, things like that, okay? So that's what we'll be working on today. So any questions before we get going? Okay, all right. So then let's get started with a review of Ohm's law. So we said that Ohm's law, there are several different ways to write it, but the way that I like to think about it is current equals voltage divided by resistance. So Ohm's law is really this relationship between these three most important quantities in electronics: current, voltage, and resistance. We said that current, what was a quick definition of current?
The flow of electricity.
Yeah, it's the flow of electricity. It's how much electricity is moving through a circuit. So it's the number of electrons per second that are flowing past a particular point. So this is how much electricity is moving. And what was a quick definition for voltage? Come on now. What does voltage do in a circuit?
The force that pushes current.
Yeah, that's right. This is the force that pushes electricity through the circuit. And what was resistance again?
The force that resists current.
Yeah, the force that resists or opposes the flow of electricity. So this is how much electricity is flowing, this is how hard you're pushing, and this is how difficult it is for the electricity to move. So really, when I look at the formula like this, it makes sense to me, because when the voltage increases, that's saying that you're pushing harder, and that makes the current, the amount of electricity, increase. So the harder you push, the more electricity you get. Kind of makes sense, right? And by the same token, when the resistance goes up, that makes it harder for the electricity to flow, and so the amount of electricity goes down. So the harder it is for electricity to flow, the less flow you get. It all kind of makes sense, right? So this is Ohm's law. Oftentimes when we write this out, we use abbreviations for these things. So we don't write current, we write I instead. And then instead of voltage, we write V, and instead of resistance, we write R. So I equals V over R here. And now, if you're a fan of algebra, you can see that we've got three different variables here. And you would see that we could kind of rearrange these to solve for any one of them. But a lot of people here are not a fan of algebra, and that's totally fine. So if you don't want to use algebra, what you can do is you can remember Ohm's law in this form: V, I, and R. And if you remember this, then you can solve for any one of these without having to do any algebra, okay? So, for instance, so the way that you do it is you write down what you're trying to solve, and then you cover that up, and then you write down what's left. So, for instance, if I wanted to solve for V, I would write down V equals, I would cover that up, and I would see it's I times R. So if I want to find the voltage, I multiply the current times the resistance. Or if I want to find the resistance, I write that down, R equals, and then I cover that up, and I see that it's V divided by I. So resistance is voltage divided by current, okay? So if you can remember this form, or at least write it down on a note card somewhere, then you can use that to solve for any one of these things, current, voltage, or resistance, as long as you know the other two. Okay? So that's what Ohm's law is. It's this relationship between current, voltage, and resistance. So any questions about that? Okay. And we said that this is really, really important because this is the foundation for understanding other people's circuits and for designing our own. So we saw how we could use this last time to pick a resistor in a circuit with an LED so that we got as much current flowing through that LED as possible without damaging it, right? So we use this to design our own circuit. And also, we can use this to understand somebody else's circuit. So if somebody else had a circuit with a particular resistor in there and a voltage source, we could use this to figure out how much current was flowing through that circuit. And then that could tell us things like how long our battery might last, or how much heat might be generated. We'll talk about heat and watts later in the semester, but it can help us to understand things like that about somebody else's circuit, okay? So this really is the most important law in electronics, and we'll be using this for the rest of the year, and really anytime we're talking about electronics. So, questions about that? Okay. All right, so then let's go on to our main topic for today, which is series circuits. So, so a series circuit is when you have two or more components connected together end to end, almost like trains on a train track. So like a resistor there, and maybe a capacitor, and an LED, and say an inductor. All of these components are connected together in series. So the definition is really two or more components connected so that the end of one component attaches to the beginning of the next with nothing in between. So nothing in between. That's really critical, okay? So we can see that these components are connected in series because the end of one component, like the end of this resistor here, is connected to the beginning of this capacitor, and there is nothing in between. There's no other component attached between them, okay? So if I have a resistor and an LED connected together like that, those are in series. if I have a resistor and an LED connected together like that, and then I have another resistor going down there, this is not series. Because there's this other component connected in between, you see? Okay? So the end of one thing has to be connected to the beginning of the next with nothing in between. So why don't we play a little game here, okay? So let's play the Is It in Series game, all right? This is a game show where everybody gets to be a contestant, and you just call out the answer when you see it, okay? So I'm going to draw a circuit on the board, and you get to tell me whether it is in series or not. So if I have a resistor here like this, and then a capacitor here like that, is that in series?
Yes.
Yes, it is, because the end of one component is connected to the beginning of the next with nothing in between. So it's not in a line like some of the circuits I drew, but that doesn't matter. That's not part of the definition. So this is in series. Yes. What if I have a resistor here, and then an inductor here, like that? Is that in series?
Yes.
Yes, because again, the end of one component is connected to the beginning of the next. Okay? So what if I have, let's say, a capacitor, and then say a resistor here, and this is connected there, and then we also have a diode over here, and that's connected like that. Is that in series? No. No. This is not in series because we've got this diode connected in between the resistor and the capacitor. Okay? So this is not in series. Okay? So let's say so what if I have a capacitor and an inductor and a resistor here and an LED or just a diode, and these are connected like that. Is that in series?
Yes.
Yes. Yeah, because the end of one is connected to the beginning of the next with nothing in between. Okay? So that's in series. What if I have 3 resistors here and they're connected together like that? Is that in series? No, because there's these other wires connected in between them. Okay, so this is not in series. So the main takeaway here is that you can have very funny shaped circuits, that can still be in series. As long as the end of one component is connected to the beginning of the next with nothing in between, those components are in series, okay? So it doesn't matter exactly what shape the circuit is in, as long as the end of one component is connected to the beginning of the next with nothing in between. Also, you could have circuits that are all in a row that kind of look like trains on a train track, but if you have things connected in the middle, those are not in series, okay? Yeah?
Is it because the electricity has to split, so some changes are going to happen? You're going to have things that are not in series?
Right, exactly. So in series circuits, all of the electricity flows through all of the components. There's only one path for it to go down. So for all of these that are in series, you can see that the electricity any electricity that flows out of one component has to flow into the next. There's only one way for it to travel. So that's another way to think about series circuits. And you can see for the ones that are not in series, the electricity does split off and go different ways, okay? So yeah, so that's another good way to think about series. Thank you. So any questions about what is or is not a series circuit? Okay, so then why do we care about series circuits? Well, in the real world, many circuits are arranged in series. So if you think about old-fashioned holiday lights, that's a common example of series circuits. If you remember those holiday lights, the end of one, they were kind of arranged in a long string. So the end of one light was connected to the beginning of the next. So you had power here, and then you had one light, and then the next light, and then the next light, and so on. And then eventually that came back here. So all of these lights were arranged in series. So that was a common example of a series circuit. Another common example is when you have speakers and you want to have several speakers attached together. You might have those attached in series. So those kind of act like resistors also. So you might have these speakers attached in series. So there are many common examples of series circuits. And so it's important to understand how those work. And so that's one of the reasons why series is so important, why we care about it. And also, even for circuits that are not completely in series like these are, many more complicated circuits include certain parts that are in series. So it's important to understand how we can analyze those parts of the circuit, even if the whole circuit is not in series. Okay? So that's why we care about this. That's why it's so important. So questions about that? Okay. So then let's talk about how we can find series resistance. Because that's the first step to analyzing these circuits and understanding how they work. So for series resistance, the total resistance equals the sum of individual resistances. Another way to write that would be R total equals R1 plus R2 plus R3 plus and on, okay? So that's how you can find the total resistance. So what this means is that if you have a circuit and you have one resistor and another resistor over here connected together, are these two in series? Yes. So the way you find their total resistances, you just add their individual values together. So if this one is 100 ohms, say, and this one is 300 ohms, the total resistance is just 400 ohms. So what that means is that if you have a 100 ohm resistor and a 300 ohm resistor and you connect them in series like this, and then you use a digital multimeter and you measure from one side to the other, you would measure a resistance of 400 ohms. So 100 plus 300 equals 400, right? So it kind of makes sense, right? When you have more resistors connected together, you get more resistance. So any questions about that? Okay. So then you might ask, well, why do we care, right? Why do we care how much resistance we have, how much total resistance we have? Well, the answer is that this can be helpful when we're using Ohm's law, okay? Because we know how to do Ohm's law with one resistor, right? We know if we know voltage and resistance, say, we can find the current. We know how to do that when we have one resistor, but we don't know how to do it with several resistors. So the way that we do it with several resistors is we find their equivalent resistance so that we get just a single resistor, and then we use Ohm's law with that. Okay? So let me show you an example of that. So Ohm's law in series. So say we have a a 10 volt power supply here, and we have say a resistor here that's 2,000 ohms and another resistor that's 3,000 ohms. We'll call this one R1, the bottom one is R2. So let's say we wanted to figure out a couple things about this circuit. So we want to figure out the total current. We'll call that I total. Bless you. So we want to figure out what the total current is. And then we want to figure out how much current is flowing through resistor 1 and how much is flowing through resistor 2. And the total resistance also. And then I R1, and then the current through resistor 2, and then the voltage for resistor 1, and the voltage for resistor 2. So we want to figure out kind of the voltage and current for every part of the circuit here. Well, that's kind of a lot of things, right? We're starting to do some more advanced calculation and analysis here. But this is the type of analysis that you might want to do on a real circuit, This will help you figure out how much current you're drawing so that you know how long a battery might last, or how much voltage is going to be at various points in your circuit. So let's see if we can work through this. Well, the first thing that we want to figure out here is the total resistance. So can we figure out the equivalent resistance? First of all, are these two resistors in series?
Yes.
Yes, they are, because the end of one is connected to the beginning of the next with nothing in between. So they're in series. So can we find their equivalent resistance? Yeah.
By summing?
Yeah, by summing them, exactly. So we say R total equals R1 plus R2. So in this case, that R1 is 2,000 ohms, and then 3,000 ohms. So R total is 5,000 ohms. So any questions about how we figured that out? Okay, and then once we know that total resistance, what we can do is we can redraw this circuit. So we can say that this circuit is just like another circuit that has only one resistor in it. As long as we pick this resistor to have the total resistance of these two, then these two circuits are going to behave in exactly the same way. So if we redraw this and say that this is a 5,000 ohm resistor over here, that's the equivalent of these two. Now these two circuits are going to behave the same way. So whatever current we had flowing through this circuit will be the same current flowing through this circuit. Okay? So, and this is really useful because now we're down to a single circuit with a single resistance. And we know the voltage and the resistance for that circuit. So now we know how to use Ohm's law with that circuit, right? Yeah.
And to find current, wouldn't you need all the totals first? Because the current is the same throughout the circuit?
The current is the same throughout the circuit. And well, now we know the total voltage and the total resistance. So we can use those two to find the total current. So yeah, so that's what we'll do right now. So remember, Ohm's law is like this. We have V, I, and R. And here, we know the voltage and the resistance, so we're trying to find the current. So we would write down I equals, then we cover that up, and we see that it's V divided by R. Okay? So that's 10 volts over 5,000 ohms. Okay? So does somebody have a calculator? Can you plug that in? What does that come out to be? So this is the total current.
0.002.
Okay, so that's 0.002 amps. So that is the total current. So we can write down the total resistance is 5,000 ohms, and the total current is 0.002 amps. So that's how much current we have flowing through this, this circuit and through this resistor. .002 amps, okay? So does anybody have any questions about how we got that? Yeah.
Just what's the math on with the 10 volts and the 5,000? Are you just dividing that?
Yeah. So this line means 10 divided by 5,000. Yep. Yeah, other questions? Okay, So, so that's the total current. So that means that that's the amount of current that's coming out of this power supply, 0.002 amps, and that's going through this resistor, and then it's also the amount of current that's coming back into the power supply. The amount of current flowing out of the power supply is always the same as the amount flowing back in. It has to be, because the current has to be replaced in this power supply. So any current that flows out has to be the same as the amount that flows back in. Okay, so we know that, and we also know that since these two circuits are equivalent, we have to have the same current over here. So that means that we have 0.002 amps over there flowing out of this power supply. How much do we have flowing back in? Yeah, the same, exactly. 0.002 amps there also. And now here's a tricky part. How much of this current flows into R1? Exactly, all of it. 0.002 amps. Because, remember, current is the amount of electricity that's flowing through a circuit. And this electricity only has one path that it can take. So all of the current, all of that electricity has to go down this path. So all of it has to go through R1. So we have to have 0.002 amps flowing through R1. And then it comes out, and where does it go? Into R2. So how much current flows through R2? 0.002, exactly. All of it has to flow through R2 as well. And then that current comes out, and then that's what flows around and goes back into the power supply. So over here, can we answer these questions? How much current is flowing through R1?
0.001.
Yeah, 0.002 amps. And how much is flowing through R2?
0.002.
Same thing again, exactly. 0.002 amps. Okay? So as somebody mentioned earlier, in a series circuit, the current is the same for all of the components because they're all connected end to end, and the current has to flow through all of them. There's only one way for it to go. Okay? So the current is the same for all of these parts. All right? Now we only have two things left to figure out. We need to figure out the voltages for the resistor 1 and resistor 2. Okay? So in order to do that, what law can we use? Ohm's law, exactly. So we're trying to figure out a voltage here. So we write down V1, say for resistor 1, equals, and then we cover that up and we see that it's I times R. So that would be I1 times R1. So what is I1, the current flowing through R1 here?
0.002.
Exactly, 0.002 amps. And what is R1? 2,000 ohms, perfect. So V1 is 0.002 times 2,000 ohms. So what does that come out to be?
4.
Okay, 4 volts. So that's the voltage across this resistor. In other words, the voltage difference from one side of the resistor to the other. So that's 4 volts. So over here, we can write that down. We say VR1 is 4 volts. And then we do the same thing for resistor 2. So we say that V2 is I2 times R2. So the current is still the same, 0.002 amps. And what is resistor 2 now? 3,000 ohms. So what is 0.002 times 3,000? So that's 6 volts. So the voltage across R2, difference from one side to the other, is 6 volts. So we can write that down, 6 volts. So that's how we can use Ohm's law with a series circuit. So you can see how we can start to analyze more complicated circuits now just using Ohm's law and our little bit of knowledge about series resistance. Okay? So the basic procedure is we look at the circuit, we find the equivalent resistance, we redraw the circuit so that we only have one resistor, and then we use Ohm's law with that simplified circuit, and then we use that information that we get from Ohm's law to figure out the voltage and current in the original circuit. So any questions about that? I know it got a little bit more complicated here today, but hopefully each step wasn't too bad. Okay? So yeah, any questions about the procedure or the math or anything like that? No? Okay, all right, so that's how we use Ohm's law in series. And we'll come back to this and we'll practice this a lot more for the rest of the semester. So if it's not, 100% clear just yet, that's all right. We're gonna do a lot more practice with this. All right, so that brings me to the engineering notation. So engineering notation is this way that we can write very large or very small numbers without having to write out tons and tons of zeros. And the way that we do it is that instead of writing zeros, we use little letters and prefixes to abbreviate very small or very large numbers. So in your lab book, there's actually a chart on page 59 that shows this. But basically, the way that this works is that right in the middle, we have units. So these are kind of standard units. This is volts, amps, ohms, things with no prefix. And then they get slightly larger. You have K for kilo. And that stands for 1,000, or 10 to the third. And then a little bigger, you have mega. That's a capital M. And that stands for million, or 10 to the sixth power. And then a little bigger still, you get giga. And that stands for billion, or 10 to the ninth power. And then there's bigger ones still. There's tera, peta, and exa. So those keep on getting bigger. And then you also have abbreviations for small numbers. So you have milli, which is a lowercase m, and that stands for thousandth. or 0.001, or 10 to the power of -3. And then a little bit smaller still, you have micro. And then this is kind of funny. This is another prefix that starts with M, but we've already used capital M for mega and lowercase m for milli. So how are we going to abbreviate this one? Well, somebody a long time ago decided, okay, we'll just use the Greek letter M. Since we ran out of English letter M's, we'll just use the Greek letter M. Problem is the Greek letter M looks like a little U with an extra tail. So this is the letter mu, which is the Greek letter M, but it looks like a U with a little tail. So that's the abbreviation for micro. So that micro stands for millionth. And that's, 10 to the power of -6. And then nano, lowercase n, that's billionth. (10 to the -9), and then pico. Trillionth. (10 to the -12). Okay, so these are these words stand for these numbers, and you've probably heard them in everyday conversation, even if you might not have noticed them or recognized them. So, like when people talk about a kilometer, that's kilometer. It stands for 1,000 meters. So a kilometer is 1,000 meters. Yeah. What's what? MA? Oh, so like when we're talking about electronics and we write MA, something like that. So that stands for, the lowercase m stands for milli, and then A stands for amps. So this is milliamps. So this is a great example. So when this is, so 1 milliamp is 1/1000th of an amp. So that's 0.001 amps. Okay. So that's a abbreviation that we see all the time in electronics. We also see kilo ohms in electronics. A kilo ohm is 1,000 ohms. So, and we also hear about these abbreviations when we're talking about computers. So you might have heard about a terabyte hard drive. Well, that's tera. It's right over here. It would be a trillion. So a terabyte hard drive means it has a trillion bytes in that hard drive. Okay? Or you might have heard of, a processor that runs at 3 gigahertz. Well, giga means billion, so that's 3 billion operations, and hertz means cycles per second. So 3 billion cycles every second. Can you imagine that? Your computer is doing 3 billion things every single second. It's just, it's staggering. So, so we also might have heard of these smaller abbreviations. So if you hear about a milliliter of liquid or a microgram of medicine, these are other uses of these same prefixes. Milli meaning thousandth and micro meaning millionth. Okay, so these prefixes pop up all over the place. We might not have noticed them before, but this is what they mean. And it's often useful or necessary to convert from one to another. So the thing to remember, the thing to know about this line is that each step on the line is 1,000 times bigger than the step to the right. So a kilo is 1,000 times bigger than 1. A mega is 1,000 kilos. Giga is 1,000 megas. So every time you go to the left, you're getting 1,000 times bigger. So from there to there is times 1,000. From there to there, that's also 1,000 times bigger. And the same applies over here. When you're going from milli to units, that's 1,000 times bigger. And milli is 1,000 times bigger than micro. So each one of these things is 1,000 times bigger than the one on the right. In other words, it takes 1,000 units to make a kilo. It takes 1,000 kilos to make a mega. It takes 1,000 micro units to make 1 milli unit. Okay? So every step here is 1,000 times bigger. So what that means is that if you are, so that tells us how we can convert from one to another. Okay? So let's say I have 5 kiloohms, and I want to know how many ohms that is. Yeah, so we know that kilo stands for 1,000, so we say that that is 5,000 ohms. Okay? So what we can do is we can say that when we're converting units from one place on the line to another place to the right, we have to multiply whatever value we start with by 1,000. So if we move one place to the right on the line, we multiply by 1,000. And so let me write that down. So to move one place to the right on the line, we multiply by 1,000. And a quick way to multiply by 1,000 is we add 3 zeros or move the decimal point 3 places to the right. So we could say move decimal 3 places to the right. But really, that's just a shortcut for multiplying by 1,000. Okay? So let's do another example. Let's say I have 3 grams, and I want to know how many milligrams that is. Well, I'm starting off here at units, and I'm going to milli. So how many places to the right am I going?
1.
So, right. And so when I move one place to the right, what do I multiply by? 1,000. So I start with 3 grams, I multiply by 1,000. How many do I get? 3,000. Perfect. So that's 3 grams is 3,000 milligrams. Okay? And if I go the other way on the line, I just do the opposite. So to move one place left on the line, I divide by 1,000. So, and a quick way to do that is to move the decimal point 3 places left. Okay, so let's do an example there. Let's say I have 6,000 6,000 megawatts, and I want to convert that into gigawatts. So how many gigawatts would that be? So I'm starting at mega, and I'm going to giga. So how many places am I going? I'm going one place left, right? Yeah, left, right here. Yeah, I'm moving one place to the left. So what do I do to this number? Divide by 1,000. So 6,000 divided by 1,000 gives me 6 gigawatts. Okay? So I'm going from mega to giga. I divide by 1,000. So I get 6,000 megawatts equals 6 gigawatts. So questions about that? All right. So then you might wonder about what we do if we go more than one place. So let's say I have 2.5 kiloohms, and I want to know how many milliohms that would be. Well, here I'm going from kilo. I go one place here to units, and then another place to milli. So how many places have I moved? Two. Exactly. So I've moved 2 places here. So every time I move one place to the right, I multiply by 1,000. So if I want to move 2 places to the right, what do? Almost. I multiply by 1,000, and then I multiply by 1,000 again. So, so I just do that twice. So, or another way to say that is I could move the decimal 6 places to the right. Okay? So if I multiply, so what I can do if I'm doing the decimal method, I start out with 2.5, and then I move that decimal 6 places to the right. So I would start here, I'd go 1, 2, 3, 4, 5, 6. It would end up right there. And then any little swish that has nothing in it, I just put a 0 there. So this would become 2,500,000 milliohms. So 2.5 kiloohms is 2,500,000 milliohms. Okay, I would get the same result if I multiply that 2.5 by 1,000 and then by 1,000 again. Okay, so that's how we do it. If we want to move 1 step to the right, we move the decimal 3 places. If we want to move 2 steps, we move 6 places. 3 steps is 9, and so on. Or you can just multiply by 1,000 that many times, once for each step. Okay? So questions about that? Yeah.
Just stuck on the part where the 2.5,
Uh-huh.
and then you're trying to find milli, am I right?
Yes, I'm going from 2.5 kilo to milli. Yeah.
Is that a K or is that an R? 2.5.
This is a K.
Oh, okay. I'm thinking it was R. I was like, where did you get the R?
Yeah, sorry. Sorry. Yeah, that's a K.
Okay. Okay, man.
Yeah. Okay. Cool. Yeah, other question? Yeah.
Is there any difference between engineering notation and scientific notation?
So slightly. So with engineering notation, you can see that each one of these is a power of 3. So so in engineering notation, we always use powers of 10 to the power, some power that's divisible by 3. Where scientific notation, it's just 10 to any power. Yeah. Yeah, other questions? Okay. So, and again, we have, for homework, the metric conversion practice on page 61 in the lab book. So there you'll get a chance to do several of these different conversions, you know, from kilo to mega or milli to micro or so on like that.
What's E engineering equivalent? Something?
Yeah, so I don't know exactly what EE stands for, but it means, it's a shorthand for times 10 to some power. So E, and that's often used on calculators. So if you have a button on a calculator that says EE, that means times 10 to something. So if you said EE6, that would mean times 10 to the 6th power. Okay? So in your book on page 59, where we have this number line, there's also that list of prefixes in a table, and it has the EE notation next to that. So for kilo, it would say EE3. For mega, it's EE6. Giga is EE9, and so on. Yeah. So other questions? Okay. All right. So then that brings me to the lab preview. Okay. So today's lab starts on page 51. And the first thing that you're going to do is you're going to open up a circuit in Multisim, and you're going to make some measurements. So the circuit is shown here, and we can get that circuit. It says it's located in LO6 series resistor lab. So if we go to Explorer here, and then we go to the instructor files, and then ET302, and then LO6.
It's LO6
Yeah,
series circuits.
yeah, and multisim. So evaluate. Okay, so this is the first circuit that we're going to look at. If we open up the meter here, this is we'll put this meter in resistance measuring mode. So if I run this right now, it's in voltage measuring mode, but we don't care about the voltage here. We're trying to find the resistance. So to put it in resistance measuring mode, I'm going to click on this little button that says omega for ohms. So I have one resistor that's 200 ohms, and no surprise, the meter measures 200 ohms of resistance, right? So I'd put that down in my lab book. Then the next part of the circuit has two resistors, and these resistors are they in series?
Yeah.
Yeah, because they're connected end to end with nothing in between. So what I'm going to do now is I'm going to measure the resistance of this part of the circuit. So the way that I do that is I click, first of all, I stop my simulation, and then I click on this wire here, and then I delete that wire by hitting the delete button on the keyboard. And then I'm going to connect a wire from this second resistor up to my meter. So now I should be measuring the resistance of this part of the circuit. So I've got two resistors in series. Each one is 1 kilo ohm or 1,000 ohms. How much should we have for the total resistance of this part of the circuit? Well, they're in series, so what do we do to find equivalent resistance when they're in series like that? We just add them together, right? So we have 1,000 ohms plus 1,000 ohms. How much does that give us? 2,000 ohms. So when I run this simulation, we should see 2,000 ohms here. Let's see. We run this. There we go. 2 kilo ohms. And we know kilo stands for 1,000, so that's 2,000 ohms. Okay? So then you'd put that in your lab book. So hopefully that's no great surprise there. So we'll come back here to the lab book. So there's 3 parts of that circuit. So you're going to measure each one. And then you're going to record the resistance here in the lab book. So you're going to put down the resistance value for each resistor. So like here, this would be 1 kilo ohm, and then 1 kilo ohm. Hopefully your writing is better than my handwriting with a mouse. And then the total resistance would be 2 kilo ohms. Yeah, question? So it starts on page 51. Yeah. Yeah. What document? The program that we were just looking at? This is Multisim, and we're looking at circuit 1A here. Yeah, so it's under instructor files, ET302, LO6 series circuits. Yeah. Other questions? All right. So that's the first part. And then the next part says you're going to change the resistances to 300 ohms and repeat. And then you're going to change to 2 mega ohms and repeat. Okay? So very similar. And then down here, you're going to look at this circuit, and you're just going to write the resistance values kind of next to this diagram here. The total resistance for each section, you just write next to that section. Okay? So any questions about that? All right. So that's the part in Multisim. And then the next part is you're actually going to build some circuits on a breadboard. So this has a quick reminder of how breadboards work. So it reminds you that on the sides of the breadboards, connections are made like this. So one component in this row would be connected to every other component in this row. Okay? So, and then there's a trough down the middle that separates one side from the other, and then the same thing goes on the opposite side. So one component in this row would be connected to another component and every other component in this row. Okay? And then the very outside edges of the breadboard go the opposite way. So they go all the way from one end of the board to the other. So if you plug in a component in a hole way down here, it's connected to every single other component in this entire row all the way down the edge of the board, okay? So that's how breadboards work. So any questions about that? All right, and then we're going to use this breadboard to make some series circuits, and then we'll actually use the meter to measure those resistances of those circuits. So I'm going to grab a breadboard here and a meter so that we can actually make a couple of these circuits.
Professor,
Yes.
LO6 doesn't pop up on my computer. Do I just have to change computers, or?
No, I'll be there. I'll take a look at this after the lecture is done. Okay, so I'm going to look at this bottom circuit here, okay? So for this bottom circuit, we have 3 resistors that are connected in series. The end of one is connected to the beginning of the next with nothing in between, okay? So the lab book asks you to build this circuit on a breadboard, and it asks you for resistance 1, resistance 2, and resistance 3 individually, and the total resistance. So in order to measure those individual resistances, I'm going to measure the resistors by themselves before they are connected to anything else, okay? So I'm going to first of all hook up my meter. So remember, when you're connecting a meter, the black lead always goes in the common port. The red lead goes in the one of the other ports. So when we're measuring resistance, the red lead goes in the right port, which is labeled V and omega here for voltage and resistance. Now, the first thing I'm going to do when I hook up this meter is I'm going to test it out to make sure that it's working properly. So I'm going to put it in the lowest resistance measuring mode, and then I'm going to connect the ends of my leads together. And it makes that horrible squealing noise, and you can see that the resistance here is less than 1 ohm. So that's a good sign. That tells me that the meter and the leads are working properly. If that was a high resistance, that would tell me that there is a problem. Either the meter was damaged or the leads were damaged. And I could go and try a different set of leads or a different meter, okay? But it's always a good idea to test out your meter first before you start making other measurements so that you know that your meter is working properly. All right, so now that I have that meter connected, what I can do is I'm going to measure my first resistor. So the way I do that is I clip one lead to one side of the resistor, and then the other lead to the other side of the resistor. And you'll notice right now, the meter is still saying OL. Anybody remember what that stands for? Overload. And that means that the thing that I'm trying to measure is too big for that particular setting. So this resistor tells me it should be about 1,000 ohms, 1 kilo ohm. And if I look at the meter, right now I'm in the 200 ohm setting. So that means it can measure values up to 200 ohms. So that's why I'm getting this overload reading. It's because the resistor is too large for that setting. So I need to move up to the next setting. So now I see a reading of 0.982 kilo ohms. Okay? So that's what I would write down. I would write down here 0.982 kilo ohms. Okay? Notice that I'm not rounding this. I'm not saying that's just 1 kilo ohm. Okay? We want to keep those extra decimals of precision. That's going to help us be as precise and accurate as possible. Also, I wrote down my units. I wrote down kilo ohms. I just didn't write 0.982 or 0.982 ohms. Either one of those by themselves wouldn't be enough information to tell me what's going on. I need to write down the units. So make sure you keep the precision and you write down the units. Okay? All right, so I do that, and then I would repeat that process for the other two resistors as well. So I'd write down the value for resistor 2 and the value for resistor 3. And then I would go and build this circuit by combining these three resistors on the breadboard. So the way that I do this is there are many different ways to make a series circuit on a breadboard, but I like to make the circuit look kind of the way that it does in the book. So I'm going to take one resistor and plug it into the breadboard somewhere kind of near the middle. And then I'm going to take the second resistor and I'm going to plug this one in so that the end of this resistor is in the same row as the other resistor. So you can see these two legs of the resistors are in the same row together. That means that they're going to be connected to each other. And then I'm going to put that resistor down somewhere over here. And then the same thing with the third resistor. I'm going to put the leg of this resistor in the same row as the second one. And then the other leg goes somewhere over here. Okay? So that's how I can connect these three resistors in series. So any questions about that? All right, and then the last thing I'm going to do is I'm going to measure the resistance of these three resistors. So I'm going to measure from one side of the circuit to the other. Now, there's a couple ways I could do this. Sort of the first way that might seem like a good idea is I can just connect the lead of my meter right onto the leg of this resistor. All right? So that's a decent electrical connection, but this is a bad idea. I almost never do this. Let me tell you why. The reason is because when I connect it like this, it's really easy to bump this cord and to yank things around, or you can even yank that component out of the board. It's really easy for this to happen, and sometimes it happens just enough so that the component still seems like it's in place, but it's not actually making a connection anymore. So that can really drive you nuts. That can take you a lot of time to figure out what's going on in your circuit if you accidentally pull things out like that, because it looks like this is in place, but now you're not making that electrical connection anymore. So I almost never connect directly to components because it's so easy to damage the circuit that way. Instead, what I do is I grab onto a wire. I attach my lead to a wire, and then I plug that wire into the board. Okay? This just makes it a lot easier. If you pull on the lead, the wire just kind of rotates around. It's much less likely to pull out of the board that way. And if it does pull out, it's easier to reconnect it. Okay? So I do that with both of my leads. I connect them to jumper wires, and then I plug the jumper wires into the board. And now, when I do that, I look at my meter, I'm trying to measure the total resistance, but what does it say?
Overload.
Overload. So what do I have to do? Yeah, I have to change the dial to the next largest setting. Because right now the most it could measure is 2,000 ohms. And what do we think the resistance should be approximately here? Yeah, about 3,000 because you have three 1,000 ohm resistors connected in series. So I move up to the next setting, and there it is, 2.95 kilo ohms. So that's what I would write for my total resistance. So again, I would keep all of those decimals. I would write, 2.95, and again, I would write my units. Kilo ohms. Yes?
For the 1, 2, 3 spot, are we measuring each individual
Resistor.
resistor?
Yes. Yeah, you measure each resistor by itself, you record their individual values, and then you record the total value there at the end. Yeah. So questions about that? All right, and then there are just a few questions at the end of the lab, so you would answer those, and then that is the end of that. So any other questions? All right, then let me take attendance, and then I'll let you go.